Okay, good afternoon again. I'm glad that we are meeting here to continue our classes in signals and systems. In the previous 3 classes that we have had, we had an introduction to what signals are. We defined signals, we classified signals, looked at the different types of signals and how they appear and exist in nature. We agreed and learned that the signals majorly exist in analog form, but also because of the difficulty in processing analog signals, it becomes important to transform these signals from their analog nature into digital signals. We looked at the structure of a digital signal processing system, moving from the analog signal to how it is converted by the analog to digital converter and how it can be processed and then converted back to an analog signal for processing. We also looked at sampling and said sampling is one of the important processes during the process of analog to digital conversion. Sampling helps us to convert an analog signal into a digital signal. We looked at the principle of sampling and the sampling theorem and said that since signals exist with a number of frequencies, the sampling theorem looks at the highest sampling, rather at the highest frequency component of the signal and uses that as a sampling frame, meaning you sample at a sampling frequency that is twice the highest frequency component of the signal that you have. So for example, if your signal has frequencies, okay? If your signal has different frequencies, for example, frequency 1, and there is another frequency 2, and then another frequency 3, but then we realize that F1 is the highest sampling, rather the highest frequency component, then your frequency of sampling Fs, okay, should be greater or twice the highest sampling frequency, rather the highest frequency component, which we are saying is F1 in this case. And we said that this frequency F1 is called the folding frequency or the Nyquist frequency. Okay, the frequency which you consider as the highest frequency component of your signal, and then sample at twice the highest frequency. Great. We now come to that time when sampled signals become important. When you sample a signal, it becomes a discrete time signal. Okay? We said we have 2 analog signal. We have 2 types of signals. We have the analog signal, which is continuous and is defined at all the time in a given time interval. But then, if you remember, we also said that this signal can be sampled on the time scale at different time intervals, and this would give us a number of samples, okay? And this would now give us a different representation of this signal, okay? And we said that the important part of sampling is the aim to recover all the signal in all the information in the discrete signal that is characteristic of the continuous signal, okay? Now this is our discrete signal. This is what we would call a discrete signal, but you realize that actually it comes from the continuous signal. We said the sampling frequency can be increased. And what happens when the sampling frequency is increased? It means that you're going to take more samples, okay? Now imagine you're taking, when you increase the sampling frequency, it means you're going to take more samples, okay? So instead of having several samples per second, you will have many more samples per second. When you finally look at this, it will definitely look even much closer to the original signal than the previous one. Mind you, you can actually increase the sampling frequency even further so that you have more samples per second. And like we said, the more the samples, the more the information that you can derive out of the sampled discrete signal, okay? The more the samples you take, the more the information you can obtain from your discrete signal. Very important indeed. And we said that by you considering the Nyquist frequency, you're aiming at making sure that you obtain as much information out of this signal as possible, okay? Of course, my lines here are not as straight, but you can tell that this now looks even more close to the analog signal as possible, okay? Great. So we are going to look at discrete time signals at this time, and we are hoping that we will understand these ones even much better, and then you know how these help us in digital signal processing. So for this chapter, in chapter 1, we introduced the reader to a number of important types of signals and described the sampling process by which an analog signal is converted into a discrete signal. That is what sampling does. Sampling helps you to convert a discrete, rather an analog signal, into a discrete signal, okay? So what is a discrete signal? We've said a discrete signal is a signal that is represented by values, where each value represents the value of your original signal at a given time interval. In addition, in chapter 1, we presented in some detail the characteristics of discrete time sinusoidal signals. And we said the sinusoid is an important elementary signal that serves as a basic building block in more complex signals. However, there are other elementary signals that are important in our treatment of signal processing. And these signals, these discrete signals, are introduced in this chapter and are used as a basic function or basic building blocks to describe more complex signals. So, in this chapter, we are saying that the major emphasis will be on characterization of discrete signals and systems, discrete time systems, and in general, we will look at a class of linear time invariant systems. Okay, we will look at discrete time. We are going to no longer talk about analog signals. We are now going to talk about discrete time signals and then the systems that are used to characterize them or process them. And we are saying that one of the key class of systems that we're going to talk about is the linear time invariant LTI system. So a number of important time domain properties of LTI systems will be defined and developed, and an important formula called the convolution is derived, which allows us to determine the output of an LTI system to any given arbitrary signal. Okay, the convolution formula we are saying is used to determine, okay, the output of an LTI system for any given input. What does that mean? If you remember, we said that a system is basically made of 3 blocks, not blocks really. However, we have an input. If, for example, I say the input is xn, we will now be talking about xn because we're talking about discrete systems. We will no longer talk about xt. And then the output is yn, okay? And this is the system. If I say the system effects a transformation t, it means that your yn is actually a result of the transformation on the input. What if the transformation was also a signal? For example, if this was hn, okay, and then you would get yn, it means that actually your yn in this case is equal to a multiple of xn, okay, when you multiply xn and hn, okay. When you multiply xn and hn, you get your output yn. This is the equation that defines your system, okay. So it means that what we are interested in from here is this multiplication that happens for us to get the result of this system. And this is what we call the convolution product, okay? The convolution, when you multiply 2 discrete signals, what you get is a convolution. And we're saying that this is very important, okay? Because it helps us to determine the output of an LTI system for any input signal. For any input signal, you can actually determine the output using this so-called convolution product, okay? So we'll proceed from here and say our motivation for the emphasis of the study of linear time invariant systems is twofold. First, there is a large collection of mathematical techniques that can be applied to analysis of LTI systems. That's important when you can actually have very many techniques that can be used or applied to a certain class of systems. And we're saying that second, many practical systems are either LTI systems or can be approximated by LTI systems. You remember we said that one of the biggest advantages of sinusoidal signals was because they could quickly be analyzed. And also that even other signals could almost be approximated to sinusoidal signals. And this is now the other important with LTI systems. Because of its importance in digital signal processing applications and its close resemblance to the convolution formula, we also introduce the correlation between two signals. So now we have two important terms here, the convolution formula and also the correlation. But like we are saying, we'll look at each one of them separately. Of course, these are related to the autocorrelation and the cross correlation of signals that are defined, and their properties will be presented. So let's dive into this second chapter. For the class of today, we are just going to explore the general structure of a discrete signal, how it can be presented, how it can be read, how it can be understood. And then we'll look at some particular types of discrete signals, the common ones, the important ones. And then thereafter, we'll also look at classification of them. And that will be it for today. Okay? So we'll start with the discrete time signal. Okay? We want to define it. We want to define the discrete time signal. Okay? We're saying that a discrete time signal, xn, is a function of an independent variable that is an integer. This n is the independent variable. Okay? No, actually, a discrete time signal xn is a function of an independent variable that is an integer. Okay? N, yes. It is graphically represented as in figure 2.1. Figure 2.1 is this. Okay? This is something we have seen before. We realize that this is characterized by values. It means that the value there is 0.9. This is the value negative 0.8. This is 0.7. This is 1.5. This is 2, 1.7, 1.0, 0.7, negative 0.8, 1.2. So it means that the signal that was sampled to come up with this discrete signal had these values at these sampling points. Very important to note is position 0 when we are describing discrete signals. There is that position where we assume the sampling to have started, position 0. Okay, then position 1, 2, 3, 4, 5. This is n. So here is n equal to 1. Okay, up to this is n equal to 5. Okay, it means that this signal exists between n equal to negative 4. Okay, and when you look at this, n equal to 5. Okay, so you can write this as xn to be equivalent to, and then you write the values from 0.9, okay, because that is the first one, up to we have 1.2, okay, and then you say that your n is defined by this, and everyone will know that at position negative 4, the function xn is 0.9, while at position 5, the function has a value of 1.5. Okay, that is actually how these discrete signals can be represented. So you can represent your discrete signal this way, graphically, graphical representation of a discrete signal. We have xn, this is the amplitude of your function, and this is n, the sample period. So if one was going to take a wild guess, okay, you could probably think that your signal, which was sampled, was probably something like this. like I told you, this is a wild guess, and you can never tell if this was actually the case. You should never assume that the value between 2 to 3 is that if this is 1 and this is 0.7, should be something like 0.8. When you put it here and when you approximate this, it may actually look relevant, but you should never be mistaken by this. This could actually be too far away from the truth. Okay? Never should you approximate this. Things of discrete signals don't work like this. I want to give you another scenario, and you will actually realize that this could have been possible. Okay? That this could also have been possible. That a situation like this is also possible. Now tell me, wouldn't this still be the sample points, even with a signal that is this wide? It is possible, okay, that actually you can have something like this, okay? You can have something like this, okay? It would still give you sample points at these points, even when actually the signal is different, okay? You can now tell that this signal would also have sampled points exactly like the first one we plotted, okay? Remember the first approximation was this. This was the first approximation that we could probably assume that our signal was this, okay? Now, don't you see significant differences? At any one time, never assume the value, okay, between 2 points, between 2 sampling points, okay? You will never know what the value was between here, and never actually approximate it, because you do not know it, you do not know what it is. Your focus will always be at the points that you have been given as the sample values, okay? This is a graphical representation of these discrete signals. We're still defining a discrete signal. Okay, it is important to note that a discrete time signal is not defined at instants between 2 successive samples. That is exactly what we have said. Between 2 samples, this signal is not defined, and you do not know what the value was, and you should not ever think of approximating it. It is incorrect to think that xn is equal to 0 if n is not an integer. Yes, that between these two, between 0 and 1, between 1 and 2, do not think that this is 0. No, it has a value, but which you do not know. It is not defined. Let's take that simple mathematical term that is not defined between these 2 sampling points. Okay, it is not defined. Okay, in the following, in the sequel, we'll assume that a discrete time signal is defined for every integer value of n. That is true, and n varies from negative infinity to infinity. For example, a case like this, your negative infinity is -4 and your positive infinity is 5. Basically, the negative and the positive are the time limits. If it is an infinite sequence, then your lower bound, which we are calling negative infinity, is -4, and your upper bound is 5. Okay, that's what we mean by from negative infinity to positive infinity. The boundaries, these 2 terms mean the boundaries. So by tradition, we refer to xn as the nth sample of the signal, even if the signal xn is inherently discrete time. If indeed xn was obtained from sampling an analog signal xa, then xn should be equivalent to xa nt. Nt means that you're taking a sampling period t, where t is the sampling period. Okay? And we defined the sampling period as the time between two successive samples. We defined that when we looked at sampling. Okay, so there are many ways we can represent a discrete signal. Besides graphical representation of a discrete time signal or sequence, there are several alternative representations that are often more convenient to use. One, we can represent it as a function representation. You say xn is equal to 1 when n is 1 and 3, and is equal to 4 when n is 2. Okay, if you are good at interpreting functions, you now see that actually this means that you have a sequence, okay, where for n equal to 1, the value is 1, n equal to 2, the value is 4, n equal to 3, the value is 1, and it is 0 elsewhere. So basically you have 0, okay, at 1, rather at 0, you have 1 at n equal to 1, okay, you have 4 at n equal to 2, you have 1 at n equal to 3, and then you have 0 elsewhere. Okay, elsewhere you have 0. And we said that we will see later on how to use an arrow key to show where 0 is, so that when you see this arrow, you know that this is at n equal to 0. Okay, this is at n equal to 0, and then you have n equal to 1, n equal to 2, n equal to 3, like that. So this is a good way of representing that. Okay, the function representation. We also have the tabular representation. You can represent your discrete signal in the form of a table. You have n, you also have xn. Okay, you have n equal to -2, -1, 0, 1, 2, 3, 4, 5, and onwards. And like we saw up here, when n is 1, the value is 1. When n is 2, the value is 4. When n is 3, the value is 1, and it is 0 for all the other values. You can also write it as a sequence, in sequence representation. An infinite duration signal or sequence with a time origin n equal to 0 indicated by the symbol, this arrow facing upwards, would be represented here as xn equivalent to, you see, 0, 0, 1, 4, 1, 0, 0, and we have the symbol, this arrow, at the point where you have n equal to 0. This is sequence representation. So a sequence xn, which is 0 for n less or equal to 0, can be represented this way. Okay, when all the values below 0 are 0, can be written as this. You have 0 at n equal to 0, n equal to 1, n equal to 2, n equal to 3, and then 0 otherwise. So this is the way you can represent your discrete signal. Okay, we are saying that these values come from an analog signal which has been sampled to give us these values. Okay, great. So we continue to say the time origin for the sequence xn, which is 0 for n, for all n less than 0, is understood to be the first leftmost point in the sequence. A finite duration sequence can be represented as this. This is important. Finite duration sequence means that its length can be defined. It means that you can define that n is between, say, for example, this is n is between -2 and up to 4. Okay, this is finite duration. You can tell the length. You can tell that we have this number of values. Okay, you can tell that you have between -2, okay, -1, 0, okay, 1, 2, 3, 4. Okay, so you can tell that this is -2 less or equal to n less or equal to 4. This is finite duration. You know the length of this. Very important. You know the length of this, and that is what we call finite duration. So we're saying that a finite duration sequence can be represented like this. We use this arrow again to show where we think our 0 point is. Okay, whereas a finite duration sequence that satisfies the condition xn equal to 0 for all n less than 0 would now be written as this. We are taking this because we have zeros everywhere behind n equal to 0. So it means that for all negative numbers, okay, the value of xn is 0. That's what we mean by n less than 0 here. So the signal in 2.1.4, this one here, okay, consists of 7 samples or points in time. So it is called or identified as a 7-point sequence. Like I said, it has a countable number of sequences. It is a finite duration sequence. Its length can be told as 7 samples. Similarly, the sequence given in 2.1.5, this one is a 4-point sequence. Its length can also be defined as 4 samples, okay? A 4-point sequence. So you can present your discrete signal this way by giving the values of your sampled signal. Again, to make this even more clear, we are saying that you're sampling a certain signal, okay? For example, this is your signal. This is the amplitude. If, for example, we say this is 1, you say this is 2, you say this is 3, and you're saying this is 4, okay? When you sample, this is your first sample, n equals to 1. You have your sample n equals to 2. You have this n equals to 3. This is n equals to 4. N equals 5. Okay? N equals 6. Maybe n equals 7. N equals 8. N equals 9. Okay? So you can give the values. Maybe this is 1.8. This is 2.2. Maybe this is 1.8 again. Maybe this is 1.9. 1.9 again. Maybe this is 3.1, and this is maybe 4.2. You know, each of these can then be given a value, and then you can represent these values on a time scale. Okay, this would be the values, and you can represent each one of them in a sequence. Okay, which would be very important. Someone is saying, please talk about the time origin of a sequence. The time origin is that time where we assume that we started sampling from. At the point when your sampling starts, that's what we call the time origin. Okay? That is where we say n is equal to 0, the value at the point where you start sampling. So let's look at some elementary discrete time signals. What do we mean by elementary discrete time signals? Maybe the most common discrete time signals. The most common, the most used, the basic time signals. We say in our study of discrete time signals and systems, there are a number of basic signals that appear often and play an important role. We are saying that they appear often and play an important role. And these signals are defined below. We have, for example, the unit sequence, okay? The unit sequence, which we denote by delta n, and it is defined as a function that delta n, the unit sequence, is 1 for n equal to 0 and is 0 for all values that are not, for all values of n that are not 0. Okay? It can be shown graphically down here that all other values that for n not equal to 0 are 0, but it is 1 when n equals 0. We're saying that in other words, the unit sample sequence is a signal that is 0 everywhere except at n, okay, equal to 0, where its value is unit. Okay, this signal is sometimes referred to as the unit impulse. That's also important, the unit sample or the unit impulse. In contrast to analog signal delta t, which is also called a unit impulse, and this is defined to be 0 everywhere except at t equal to 0, that's in time domain, and has a unit area. The unit sample sequence is much less mathematically complicated. A graphical representation of this is shown here. It is only 1 at n equal to 0 and 0 elsewhere. Number 2, the other sequence that we have is the unit step sequence denoted as un, which is defined as 1 for all n greater or equal to 0 and 0 for all n less than 0. What does that mean? That actually, okay, if we say that this is n equal to 0, okay, the values below 0, this function is 0, okay, but when the value reaches 1, every one of the values above this becomes 1. You see that? Okay, 0 for all values below 0. This is 1, 2, 3, 4. This is n equal to 4 onwards, but everything else is 1 above 0, but is also 0 below 0 for the value of n. That is the unit step signal. We're looking at the common signals. Okay, then this is how we graphically represent the unit step. Every other value below 0 is 0, but then all values above n equal to 0 are 1. Okay, number 3, we have the unit ramp signal. We are talking about the common signals. This is the unit ramp signal denoted as URN, which is defined as n for n greater or equal to 0 and 0 elsewhere. What does that mean? When you look at that, it means that, okay, if this is your 0, okay, it means that all values below 0 are 0, and then n is equivalent to the sampling value. So at 0, it is 0. At 1, it goes to 1, okay? At 2, it becomes 2, okay? At 3, it becomes 3. At 4, it goes to 4, okay? See? At 5, it becomes 5. At 6, this becomes 6, okay? If this was a continuous signal, if this was continuous, this ramp would look like this, okay? I've just missed this. It would look like this. See, a ramp indeed. That is what we would have. That is your unit ramp. But when you look at it as a discrete signal, you see how these things change. The next common signal is the exponential signal. We all know, or we can remember some exponential signals in time domain, okay? We have different exponential signals. We have a growing exponential, something like this, okay? We also have a decaying exponential, like that. There are many types of exponential, okay? So the exponential is a to the power of n for all n. If the parameter a is real, then xn is a real signal, okay? And we're saying that the figure 2.15 illustrates xn for various values of parameter a. Here, I think this is the graphical representation of the unit ramp. Indeed, the unit ramp, figure 2.15 is down here. This is what I was talking about, different exponentials, okay? Exponential signals down here. So this is the value of a. When a lies between 0 and 1, if it is 0.3, 0.5, 0.7, this is a decaying signal, okay? If a is less than 1, rather a is greater than 1. When a is greater than 1, then this is a growing exponential. When a lies between -1 and 0, then you have your signal like this, okay? And likewise, when a is less than -1, this is what you get. But you know why we have these interchanging values is because if, for example, we say a is equal to, for example, here we have -1, this or equal to, okay, so we say a is equal to -0.2. You see, when you put this to the power of 1, it becomes a negative value. When you raise it to the power of 2, it becomes a positive value, but which is lower than this. You see this? When you put it to the power of 3, it becomes negative again. But when you raise it to the power of 4, okay, again it becomes positive, but definitely is much smaller. Okay, so that's how we keep getting the values of this exponential function to be like this. If this was sinusoidal, you would be seeing a sinusoid running between these two where it would be an alternating sinusoid, something like this, if it was a sinusoid. Likewise, it's the same for this. This would be a growing sinusoid. Okay? See this? Again, let's remind ourselves that these are samples. So definitely, these would have been samples of this kind of exponential signals. So that's an illustration of an exponential signal, a to the power of n. Okay? If a is complex, then this is what you would have. But you know that complex exponentials can be written using Euler's formula in this form. Okay? And we're saying that since xn is now complex valued, it can be represented graphically by plotting the real part, Rn cos theta n, as a function of n, and separate plotting the imaginary part. And that's what we are having here in these exponential illustrations. Okay? The next thing we want to look at is basically the classification of discrete signals. Classification. Which classes do we have, or what types do we have of these discrete signals? Okay? We definitely classified continuous signals, and it would be in order to classify discrete signals. So we are looking at classification of discrete signals and the mathematical methods employed in the analysis of discrete time signals and systems depend on the characteristics of the signals. So in this section, we classify discrete time signals according to a number of characteristics. Okay? And we are starting with energy signals or power signals. When do we say that this is an energy signal, and when do we say that this is a power signal? Is this something you have seen before, or is this very new to you? Okay. The mathematical methods employed, we have said, for this analysis of discrete time signals and systems depends on their characteristics. Okay. And we are saying that we can start with energy signals and power signals. An energy signal E of a signal xn is defined by this, that the energy signal is the discrete sum of the squares of the magnitudes of the components. Okay? When you take the sum of the squares of the numbers in the sequence, what you get is an energy signal. Okay? What does an energy signal mean? We have used the magnitude squared values of xn so that our definition applies to complex valued signals as well as real valued signals. So the energy of a signal can be finite or infinite. Finite, if E is finite, that is if it has a range from 0 to an upper range, then xn is called an energy signal. Sometimes we add the subscript x to E, okay, and write ex to emphasize that ex is the energy signal of the signal xn. Okay, all the same, we see that we are taking the square of the signals, rather of the values in the sequence to get the energy signal en. Okay. Okay, this is the real part and this is the imaginary part, but we are talking about, this was previously, the graph of the real and imaginary components of a complex valued exponential signal. So we can define an energy signal. Okay, we can define an energy signal, and we are saying that clearly if E is finite, then P is equal to 0. On the other hand, if E is infinite, then the average power P may either be finite or infinite. If P is finite or non-zero, the signal is called a power signal. Okay, a signal whose power is defined is non-zero is called a power signal. Okay, right. We have to also be a little bit fast. There are people watching Olympics where I am, and we might have distractions. Someone says Cheptegei has broken another record now. So people are watching Olympics in class as well. So I shouldn't complain. Okay. Periodic signals and aperiodic signals. This is the next class of signals that we are seeing, periodic and aperiodic. Okay, periodic signals and aperiodic signals. This is the next class we are looking at. All of us understand when we say something is periodic and when we say something is aperiodic, especially in dealing with sequences. Periodic, we said that a signal is periodic if it has a time t after which it repeats itself, and it is aperiodic if it lacks that characteristic. If there exists a period time t after which a signal repeats itself, then we say it is periodic. We have said previously that sinusoidal signals are periodic. Though mine here may not be periodic because it's not as linear as it should be. Okay, but we have also said that we can have signals that really lack anything that looks like they repeat themselves, so they are aperiodic. Okay, so we are saying that a signal xn is periodic with a period n. Of course, the period is greater than 0 if and only if x at n plus n is equal to xn, meaning that if you have a value at xn, when this n is increased by n, then the value is the same. Okay, we have seen that in sinusoids, that if you have this as your sinusoid, okay, and you take a value here, then if the period is 2 pi, you will find that after 2 pi it will be the same value, and after another 2 pi it will be the same value altogether. That's what we are saying about periodic and signals being or having the characteristic of periodicity. Okay, the smallest value of n for which this equation holds is called the fundamental period. We have seen that it is called the period, but basically we refer to it as the fundamental period. Okay, if there are no values of n that satisfies this equation up here, then the signal is said to be non-periodic or aperiodic. Okay, we have already observed that the sinusoid signal of this form is periodic when f naught is a rational number. That is, if f naught can be expressed as f naught equal to k over n, where k and n are integers. We saw this previously. The other class of signals is this: symmetric and antisymmetric. To state it more simply, we can say even and odd signals. So some signals can be even, while others can be odd. Okay? Even and odd signals. So a real valued signal xn is called even if x at negative n is equal to xn. I want to give a typical example. Okay, when you have, for example, this as your n equal to 0. Okay, if you have a signal that is something like this, or this is not exactly what I wanted to put. First, please forgive my using an analog signal. Okay, but if you have a signal that is like this, so that if you sample it, you may have these values here. These are your samples. You have these as your samples. Okay, you realize from here that actually the values, if this is -1, this is -2, the other is -3. You have 1, you have 2, you have 3. Okay, realize that x -1 is equal to x1. Okay, this value here is equal to here, and x -2 is equal to x2, and x -3 is equal to x3. Okay, because these values here would be the same. This is called an even signal. But we have also seen signals that have, for example, this formation. Okay, such that if this was 1 and this was -1, okay, x -1 is equal to -x1. Okay, again x -2 is equal to -x2, and x -3 is equal to -x3. A signal like this is said to be odd. Okay, so you can define even and odd signals this way, that you can classify even and odd signals this way. And that's what we are saying here, that if a signal has the characteristic that x -n is equal to xn, it's said to be even. But if it is x -n is equal to -xn, then it is said to be odd. We can illustrate that one here. This is an even signal, while this is an odd signal. Okay, this is even, this is odd. Great. And you can mathematically represent an even signal this way and an odd signal this way. And the one signal can actually be a sum of both the even and the odd signal. And that was the purpose of today's class. Introduce discrete signals and also show different types of signals, and also show how different discrete signals can be represented. When we meet next time, we will look at manipulation of discrete time signals. How can you manipulate the time component? How can you shift it? How can you fold it? How can you reflect it? Okay, those things. How can you multiply? How can you add? How can you scale a sequence? Okay, and then we also look at discrete time systems, and yes, that will mean that we will actually be progressing, moving in the right direction. We also classify systems, definitely. And we said that for this course, we are going to do chapter 1, chapter 2, and chapter 3. From the look of things, we are lagging behind because this is the 6th week, meaning we have 7 weeks of teaching, and maybe we have to increase speed when we start meeting next time, okay? Because we have to cover this work. I know how challenging all these things sounds, okay, given the resources available and of course the inconveniences that come with doing this thing at a distance. But we have been saying all along, we have agreed previously that every crowd has a silver lining. Time will come and all this will end and we will be good to go again. Okay. If anyone has any question, you may raise your hand up, and in case there are no questions, then we may close this class. Please go through the content of today and let us meet again next time. Thank you very much.